Today we're going to talk about integration by substitution. Remember that from our rules of derivatives, if we have that capital F prime of u is equal to little f of u, then the derivative with respect to x of capital F of u of x is equal to capital F prime of u of x times u prime of x. That's simply the chain rule. And since capital F of x is equal to little f, that's f of u of x times u prime of x. So if we have something that is a composite function multiplied times the derivative of the inside function, then we can simply undo the chain rule and have the antiderivative of f at u of x plus c. And again, people frequently go, well, where does this go? Well, this was formed by taking the chain rule and multiplying by the derivative of the inside part. So when you undo the chain rule, it goes back away. So for example, on this problem, the integral of 1 plus 3x squared times cosine of x plus x cubed. If you recognize that, and I'll rewrite this as, I'm going to put a big set of square brackets, cosine of x plus x cubed, bless you, times 1 plus 3x squared dx. Notice that the 1 plus 3x squared is exactly the derivative of the inside part. So all we need to do is take the antiderivative of the outside part and leave the inside part alone. Well, the antiderivative of cosine is sine. So this is going to be sine of x plus x cubed. And because this is an indefinite integral, we need to give the general solution plus c. And there are a lot of problems where this is all you're going to have to do is undo the chain rule. But sometimes it can be a little trickier than that. So when it is, sometimes the function that we have outside is not exactly the derivative, but somehow we can make it a multiple of the derivative. Well, if we can do that, we can kind of do the same thing. Now, on this next problem, could you just undo the chain rule on this? Absolutely. I fully understand that you could do this by undoing the chain rule. What I want to do is do it by the method of substitution to show you how the method of substitution works. Okay, so for this problem, if I was doing this on a homework set, I would absolutely not use substitution because I can do it faster just by going, oh yeah, the derivative of my inside function is this function. So this is just going to be tangent of x to the fourth plus 3, done. Plus a constant, of course. Here's how the method of substitution works. We're going to let u be equal to almost always, but not quite. We're going to almost always let u be equal to the inner part of the composite function. Then we'll take the derivative of both sides with respect to x. So that'll be du dx is equal to, God bless you, 4x cubed. If you multiply both sides of that by the differential dx, you have du is equal to 4x cubed dx. Notice that that is this and this part, both the 4x cubed and the dx. is equal to du. So what I'm going to do is write a simpler looking integral. I'm going to have the secant squared of, I'm going to replace the x to the fourth plus 3 with u, times everything else that's left, which was just du. So now we just take the antiderivative of secant squared with respect to u, that'll be tangent of u, plus a constant. And much like when you borrow something from someone, you want to return it to them in the same form that you got it in. I want to replace the u with x to the fourth plus 3 so that it's in terms of the same variable it was to start with. Any questions about that? So by doing this u substitution is what it's typically called, we've made my integrand a lot easier to look at. Okay? And there are times when I do it when it's just really ugly, I go ahead and do that just so I can look at something that's not quite as spread out all over the place. It used to be on the AP exam that there were no problems that you couldn't, if you really thought about it for a little while, do by undoing the chain rule. That is no longer true. And I'll show you an example of that in a minute. All right, page 2. Take, for example, this problem. I'm going to show you how to do it by u substitution, and then I'll show you on this one that you could do it another way without doing a u substitution at all. So I've got a composite function. What is the derivative of of x squared plus 9? Don't everybody jump at once. It's 2x. Is that a multiple of this x that's out here? If that's the case, we can almost always use u substitution. Actually, you can always use u substitution. I should say it that way. So I'm going to let u be equal to the inside part of my function, x squared plus 9, the inside part of the composite function. Take the derivative with respect to x. We get 2x. I notice here that I'd like it to be x dx, right? So I'm going to multiply both sides by dx and divide both sides by 2. That'll mean that 1/2 times du is equal to x dx. So now my integral becomes the integral of u to the 5th times 1/2 du. So then I'll keep the constant multiple 1/2. The antiderivative of u to the 5th is 1/6 u to the 6th plus c. So this is 1/12 of x squared plus 9 raised to the 6th plus c. Now, how could you do that without doing any of that? Well, what you could do is this. Start off with the same integral. And honestly, on problems like this is what I do. I can't be bothered doing a u substitution on this. I really don't want this to be x. What do I really want it to be? 2x. All right, I'm going to multiply it by 2. Well, if I do that, I've changed my answer, haven't I? So to counteract that, I'm going to multiply by a half. But the 1/2 I'm going to put in front of the integral so that I can just go, oh, I can just undo the chain rule here. I'll keep the 1/2. Undoing the chain rule, this is going to go, this 2x factor is going to go away. I'll have 1/6 of x squared plus 9 to the 6th plus c. So it's 1/12 of x squared plus 9 raised to the 6th plus a constant.
Why the 2x go away?
Because if I think about taking the derivative of this, the 2x comes from doing the chain rule, right? When I take the derivative. So when I undo taking the derivative, the 2x goes back away.
So this whole process is antiderivative?
We're doing antiderivatives. And you can always check it to see if it's correct by taking the derivative. You good? Okay. All right. Let's take a look at this one. I would very much rewrite that to start with. This would be x cubed plus 3x squared plus 12 to the negative 6th times x squared plus 2x dx. I'll leave it up to you guys. Do you want to do a u substitution, or do you want to try and see if we can do it by undoing the chain rule?
Seems like a trick, and it's not actually doable by chain rule, by undoing chain rule.
Oh, no, it absolutely is. No, I promise, it really is, and it's not horrible.
Well, let's do that.
Yeah.
Okay, so what is the derivative of my inner function here?
3x squared plus 6x.
So that's what I want this to become. How can I make that
Multiply by 3.
multiply by 3? So to counterbalance that,
1/3.
got to multiply by 1/3. So this is 1/3 of the integral of x cubed plus 3x squared plus 12 to the negative 6th power times 3x squared plus 6x dx. Well, now this is the 3x squared plus 6x is exactly the derivative of the inner function, so I simply undo the chain rule. I'm going to have 1/3 times negative 1/5 of x cubed plus 3x squared plus 12 to the negative 1/5, or should be negative 5, plus c. And I would just simplify the constant, make it 1/15. So it's negative 1/15 times x cubed plus 3x squared plus 12 to the negative 5 plus c. Not so bad. And again, a lot of them will be that way, where you can, if the derivative of the inside part is here in some multiple form, multiply by 3, multiply everything by a half, something, then you can always do it by undoing the chain rule. All right, here's a problem where we've got difficulties. Because you're like, okay, well, if I made the inside part is 3 theta, right? The derivative of 3 theta is just 3. I could take care of that. Unfortunately, do you know the antiderivative of tangent?
No.
I do, but only because I cheated and looked ahead. So the question becomes, well, is substitution actually helpful on this? And the answer is yes. What I'm going to do is rewrite tangent in terms of two functions that you know very well,
Sine and cosine.
sine and cosine. So I'm going to
Yay.
rewrite this as the integral of sine of 3 theta over the cosine of 3 theta d theta. And then I'm going to rewrite that as a composite function times another function. You're like, what composite function? I'm going to rewrite this as cosine of 3 theta to the negative 1 power times sine of 3 theta d theta. So now I have a composite function times another function. What's the derivative of the inner function?
Three.
Wait a minute. I'm getting lots of input and I can't separate them.
3.
The other function is 3 theta.
So this is going to be, the derivative is going to be what? What's the derivative of cosine of 3 theta? It'll be,
-3 sine.
no one has quite said it right yet, at least according to my ears.
Sine 3 theta.
There we go, negative 3 sine 3 theta. Right? Well, that's just a constant multiple different than this. So I'm going to multiply by negative 3. So I'm going to multiply by negative 1/3. The integral, and be sure that you keep the integral on here. Sometimes when we're doing work with the integrand, people get so excited about that they forget that they haven't actually taken the antiderivative yet. So I'm going to have negative 1/3. What is the antiderivative of something to the negative 1 power?
0.
It's the natural log. Very good. So this is going to be the natural log of the absolute value of cosine of 3 theta plus c. In general, and you should probably add this to the list of things that you have memorized, the integral of tangent of x dx is the natural log of the absolute value of cosine of x plus c. That should be negative natural log, absolute value of cosine of x plus c. I will say occasionally books will go, oh, well then I could put the negative 1 back as an exponent on the cosine. Cosine of x raised to the negative 1 power is 1 over cosine, which is secant. So sometimes you'll see it written this way. The natural log of the absolute value of secant of x plus c. Both are acceptable. It's partly why you don't see these a ton on the AP exam, because some people teach it one way and some people teach it the other. I'm like, well, you should recognize that they're the same, but all right. So that's a handy thing. We didn't know the antiderivative of tangent before, now we do. Now, this last problem. This is a problem where with all the other ones we can do some finagling and undo the chain rule. Not so much on this problem. So I'm going to start by rewriting it as 5x plus 1 to the 1/2 power times x dx. The derivative of 5x plus 1 is 5. Is this outer function a multiple of that?
No.
No, it is not. However, substitution still works. I'm going to start off the same way. I'm going to say u is equal to 5x plus 1. Let u be equal to the inner function of your composite function. Take the derivative with respect to x. Du dx then is 5. So du is 5 dx, which means 1/5 du is equal to dx. And everything's still pretty good, except that we've got something to go in dx's place. We've got something to go into the 5x plus 1's place. We don't have anything to go in the x's place yet. Well, if u is equal to 5x plus 1, then u minus 1 divided by 5 is equal to x. So now I can substitute. I'm going to replace the x by u minus 1 over 5 times u to the 1/2. I'll replace the dx with 1/5 du. A lot of fractions going on there. I'll go ahead and pull out the fractions. I have a 1/5 times 1/5, so that's 1/25 times the integral, and I'm going to distribute the u to the 1/2 times the u minus 1. U to the 1/2 times u to the first is
0,
is what I heard. U to the 3/2, thank you, minus u to the 1/2 du. We'll take the antiderivative with respect to u, so that's 1/25 times, what'll that be, 2/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. I will say, if this is, and this would be one that would be a good multiple choice question on the AP exam, they're going to factor out a 2, and they're also going to factor out a u to the 3/2. They're almost always going to do both of those. So that's going to be 2/25 u to the 3/2 times 1/5 of u minus 1/3 plus c. And then, of course, put everything back to x's. So that's 2/25 of 5x plus 1 to the 3/2 power. They might, because it was given as a radical, change that to 5x plus 1 cubed, take the square root of all of that. Then times 1/5 of 5x plus 1 minus 1/3 plus c. And if they're feeling especially perverse, they'll go ahead and distribute the 1/5 and collect like terms. So that's going to be x 1/5 minus 1/3 is negative 2/15. Right?
So this is why we don't simplify on tests.
Yeah. So on a test, if you didn't factor out the u to the 3/2, I wouldn't be upset. Just know that if it's a multiple choice, it's likely to have that done. But once you get it to here, where you've got it back in terms of x, yeah, you can leave it like that. Yes, sir.
Oh, I know it now.
No worries.
I just
Any questions? Okay. Yes.
Back on the last question, when you said the integral of tangent of x dx was equal to the negative natural log of the absolute value of cosine of x plus c, why was it the negative natural log for cosine but positive natural log for secant?
What? What's secant? There's no secant in this anywhere.
No, I mean on the. I mean.
No, please go ahead.
This,
I see what you're saying. Gotcha. So you've got negative natural log of the absolute value of cosine of x plus c. And I said it, but I didn't show it. That would be the natural log of the absolute value of cosine of x raised to the negative 1 power plus c. That's one of those properties of logarithms. And then this would be 1 over the absolute value of cosine, which would be the absolute value of secant of x. That's why. Sorry, I was like, what? I wasn't following you at all. And I said it, but I didn't write it. I should have written it. And the reason that some people teach this one is because it is slightly simpler because it doesn't have a negative. I usually do this because I'm thinking about how I got it. Okay? Sorry I didn't follow you at first.